What is going on, guys? Welcome back. This video today is going to be an advanced NumPy crash course, which means we're going to go more into the details and advanced aspects of the NumPy library, and we're going to learn about things like vectorization, advanced indexing, broadcasting, views versus copies, and so on. So it's going to go into the more nuanced things, into the more advanced things, and we're not going to cover the basics like what are arrays and how to work with them and what are shapes and how to do basic operations. If you are interested in any of that, I already have a NumPy crash course on this channel. You can watch that for beginners. This is going to go more into the details, into the depth of NumPy. So let us get right into it. Now, I want to get started right away with the first concept for this course, which is broadcasting. And broadcasting is what NumPy does when you perform an operation involving two arrays with differing shapes when the shapes are still compatible. So for example, let's say I import NumPy as NP here. If I have an array and let's say this has three elements here, 1, 2, 3, this array here has the shape 3. In NumPy, it's written like this. It's a tuple with one element, so 3, and that means it's a one-dimensional array with 3 elements. Now, if I have a second array, B, with the exact same shape, let's say we have different values, 4, 5, 6. If I perform an operation, now these are basics, you already know this if you're watching this, we perform an element-wise addition. So we have 5, 7, 9 because we add 1 to 4, 2 to 5, 3 to 6. This is the result. Now, broadcasting is what happens when you have differing shapes. For example, if I change the shape of this here to 1 by removing 2 elements, now we have different shapes. So I have to add a NumPy array of shape 3 with a NumPy array of shape 1. And how is that handled in NumPy is by doing broadcasting. Broadcasting means we're repeating the elements across an axis. So in this case, what we would do in order to make this addition possible is we would say that we just repeat the 4 3 times, because now B is again of shape 3 and we can do the addition easily. Now we did this manually here, so we get 5, 6, 7 because 1 plus 4, 2 plus 4, 3 plus 4, but NumPy does this using broadcasting automatically. So if I do it just like this, and if I say that this has the shape 1, I still get the same result because B is being broadcast across A in order to make the shapes compatible. Now this gets more interesting when you get to higher dimensions. So if I have A being equal to this and B being equal to an array where I have maybe multiple dimensions, so let's say I have 4 here and 5 here in separate lists, now B has the shape 2, 1. Why? Because I have two lists two lists containing one element. So 2 times 1. And this is 1 times 3, or actually it's just 3. Now to make this compatible, if I add A to B, what NumPy is going to do is it's going to turn this into 1 and 3. Meaning it's going to add an extra dimension around it. So it's going to turn this into this. And because of that, this is now going to be compatible. These are the rules of broadcasting. In general, compatibility with shapes is you either have the same number on the axis, so the same shape on the axis, or you have a 1 in one of these shapes. So in this case now 1 and 2 are compatible because 1 is always compatible, and 3 and 1 are compatible because 1 is always compatible. If I have a very high dimensional array, let's say something like this here, maybe like this, then a compatible array would always either have the same value or a 1. So for 5, 5 would be compatible. For 1, any value is compatible, 9 for example. For 6, either 6 or 1. If I have 1, it's compatible. For 7, if I have 7, it's compatible. For 9, I can have 1. For 10, I can have 1. For 2, I can have 2. And for 1, I can have whatever. So these two would be compatible, these two shapes, because it's always either the same number or it's a 1. And because of that, these are compatible. Now, if we start out with an array of shape 3, that is by default not compatible, but what makes it compatible is that NumPy reshapes it into 1, 3, and now 1, 3 is compatible with 2, 1 because 2 and 1 and 3 and 1 are compatible. So what happens when we perform this operation is actually that both of them are being broadcast across different axes. So what happens here is, first of all, it's turned into 1, 3, like this. And then we can see, okay, I need on this axis here, I need to get 1 to be equal to 2. So what I do is I duplicate this row. So I basically do it like this. I turn this into 1, 2, 3, 1, 2, 3. Now it has the shape 2, 3. So these are now the same. The problem here is that these are not the same yet. So I need to make the inner dimension equal here. So what I do here is I multiply, or I repeat this 3 times. So I turn this into 4, 4, 4, 5, 5, 5, and now we have the same dimensionality. Now we have the exact same shape, and now if I do the addition, what happens, a plus b, is I get 5, 6, 7, 6, 7, 8. The exact same thing would happen if I leave the default. So if I have what I had in the beginning, 1, 2, 3, and 4, 5, like this, the whole broadcasting that I now did manually will be done by NumPy. So if I say print a plus b, remember the result, 5, 6, 7, 6, 7, 8. Run this, 5, 6, 7, 6, 7, 8. The exact same result because NumPy does this already automatically by broadcasting. So you can see that this compatibility that I explained before is the case if you try to do this with randomly generated arrays of very high dimensionality. If I say x equals, or let's go with a np random, this function allows me to pass a shape to it, and then it just generates random numbers. So if I do something like 5, 7, 1, 4, 8, 1, 2, and then I have a second array b, and I have a compatible shape. Let's go with 5, 1, 8, 4, 1, 5, 1, for example. Then I can do the addition. So I can do a plus b and everything works fine. You can see this is a very high dimensional array, but it works. These two are compatible even though the shapes are very differently. Why? Because 5 and 5 is compatible. In this case now, this is going to be broadcast across this axis. So we're going to multiply, or we're going to repeat 7 times on this axis. We're going to repeat these here 8 times on this axis. These are already compatible. We're going to repeat 8 times here, 5 times here, 2 times here. And then we're going to have the exact same shape, which we can actually see if I type .shape. You're going to see the resulting shape is just 5, 7, 8, 4, 8, 5. So 5, 7, 8, 4, 8, 5, 2. That's exactly what's happening when you broadcast these values. Now, if you change any of that to something that is not compatible, for example, 7 and 5, this is not going to work. We're going to get the error. Operands could not be broadcast together with these shapes. And also, it doesn't work if it's a multiple. So even if I say something like 4 and 2, it still doesn't work. You cannot just multiply it twice now, or repeat it twice. It doesn't work like that. You have to have either a 1 or the same number. This is how broadcasting works. Now, the next thing I want to talk about is advanced indexing. Now, let's say we have an array here, which is multidimensional, or maybe let's start first of all with a simple one. Let's say np array 1, 2, 3, 4, 5, 6, 7, 8, 9. Basic indexing, we already know about this, is I can say, give me the first element. So A0, for example, or give me the first element up until the fourth element. So 1, 2, 3, 4. Or I can also say, give me the first up until the ninth element with a stride of 2. So I will get every other element, 1, 3, 5, 7, 9. This is basic indexing. And this can also be done with multidimensional arrays. So if I have, for example, here a list of lists where this is my structure. So I have these here and then a final bracket. So let me just add a comma here like this. Now we have an array where I have 3 lists with 3 elements, or a 3 by 3 array. And here I can also do basic indexing. I can say A0, 1, which would give me the first row, second column, which is the 2 here. And I can also use slicing here. So I can say 0 to 2, which would give me the first 2 rows. So this is basic indexing. Now, advanced indexing can be done by passing a list. So basically, if I say, first of all, what I can do is I can pass a tuple to have the exact same effect as passing the individual or specifying the individual indices. So if I say A01, it's the same as passing a tuple with 0, 1 in this case. So it's the same as saying A0 and then square brackets and then 1 square brackets. This would give me the same thing as passing the tuple. But advanced indexing happens when I pass a list. So when I pass, instead of a tuple here, I use square brackets. Now something different happens. So now I'm selecting specific rows. In this case, now what I'm doing is I'm not selecting first row of second element. I'm selecting first row and second row. And I can change that to 2. And in this case, it would select first row and third row. So the last row. these two, as you can see, 1, 2, 3, 7, 8, 9. But before we get into more of that, I want to show you what dimensional indexing is. So dimensional indexing is you can select everything across a dimension. So if I say, for example, let's delete this here. If I say, for example, I want to have from A, I want to have everything. How I can do that is I can pass a colon for the first dimension and a colon for the second dimension, which would mean give me everything from this array. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if I change one of these colons to a value, for example, to 1, what happens here now is I want to get all the rows, but I want to get only the second column. So for each row, this is why I have the colon, across the row dimension, I want to have everything, so all these rows, but I only want to have the second column, so the column with the index 1, 2, 5, 8, which is what I get here. I can also do it the other way around, which is the equivalent of just selecting the second row. So 4, 5, 6. This is how you can do that with dimensional indexing. Now, what you can also do here is you can add new axes. So you can add an additional axis around this selection, which can oftentimes be useful when you're working with some deep learning frameworks or some machine learning models that want to have a certain shape or a certain dimensionality. You can oftentimes or you will oftentimes need this because an extra dimension, for example, is required. So what I can do, for example, is I can say give me the second column, 2, 5, 8, and then I can add a vertical dimension, for example, by saying np new axis. This adds a new axis to the selected array, and now you can see instead of having 2, 5, 8 in a row, I have them here across a new axis that I added. Now it depends on where you add this new axis, because if I add it in the beginning, I'm going to get a horizontal axis. So I'm going to get np new axis, and then I will get it like this, an extra dimension around it, but horizontally. And if I do it at the end, I get it vertically. So this is also something that can be quite useful, as I said, for certain machine learning models, frameworks, whatever, for shape compatibility or dimension compatibility. So that's dimensionality indexing or dimensional indexing. Advanced indexing itself is all about selecting specific aspects of an axis. So if I say, again, if I say 0 and 1, it doesn't mean, or 0 and 2, it doesn't mean give me row 1 and position 3. It says give me row 1 and row 3. So row 0 and row 2, actually. We can also do that in combination with the dimensionality indexing. So if I say give me every row, but give me only the first and last column, I can do it like this. So I can say A, every single row, but the columns 0 and 2. So I only get 1, 4, 7, 3, 6, 9. As you can see, 1, 4, 7, 3, 6, 9. Selected like this. I can also do the same thing with two lists. So I can pass here 0, 2 and 0, 2, which would mean first row, first column, second row, or not second row, last row and last column. So in this case, I get 1 and 9. So I only get 1 and 9. First row, first column, last row, last column. And I can also do the same thing to select all the diagonal elements. I can say 0, 1, 2. And I can also, of course, do this with different values. So I can say 0, 2, 2 here. So in this case now with the 1, I got the diagonal elements. If I set this to 2, I will get 1, 6, 9, because now I'm selecting first or second row and last column here instead of second row, second column. So you can do it like this. Another way of advanced indexing is Boolean indexing. So what we can do here is we can pass Booleans to say what we're interested in. For example, I can say true, false, true to select the first and last row. This would mean, okay, I get the first row, yes, not the second row, which is why it's false, and yes, I also get the last row. Of course, this can also be combined here with dimensionality or with dimensional indexing, which would do the same thing for the columns now. So I get yes, the first column, yes, the last column, but no for the second column. And I can also do a sort of Boolean masking where I pass another dimension here. So I say, for example, true, 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 and then maybe true, false, true, and then in the end, true, true, true again. This would now mean that for every single element here, I have a true or false value. In this case, now everything is set to true except for this one, which is the 5. So if I run this now, I get 1, 2, 3, 4, 6, 7, 8, 9 without the 5 because I masked it or I indexed it as false here. And I can also do the same thing with the 9 if I want to. Now I'm going to get just 1, 2, 3, 4, 6, 7, 8. So yeah, if you want to see more about this, for all of these topics that I'm covering here, I'm not going to explain every single detail about them. So if you want to see more about this, you can go to the NumPy documentation. I think for broadcasting, I'm going to actually open up the links here so you can see them. For broadcasting, there's a documentation page that you can look at. And for what we did right now, the advanced indexing, there's also a separate documentation page. So just go to the NumPy documentation for all the nuances, all the details. It would just take forever to cover absolutely everything. So I want to give you a good overview, and this is how you do advanced indexing. All right, now the next thing I want to talk about is sorting and searching. So how can we sort NumPy arrays is the first thing. As you can see here, I messed up the order of the elements a little bit, so we want to sort them. We want to get them into a specific order, and you can do that in NumPy in two ways. You can either use the np sort function, or you can use a.sort, so your array.sort. The difference here is that np sort returns a sorted version of the array and doesn't apply the sort to the array itself, whereas a.sort sorts the array. So after calling a.sort, your array is sorted in the specific way that you sorted it in. So np sort doesn't really change the array unless you save the result into the array. So for example, let me show this. If I say print np sort a without specifying anything else, you're going to see that something has changed. Now it doesn't have the exact same structure as before, so it's not 1, 2, 3, 4, 5, 6, 7, 8, 9, but you can see that it's sorted per row. So 5, 9, 8 turned into 5, 8, 9. 4, 1, 6 turned into 1, 4, 6, and 7, 3, 2 turned into 2, 3, 7. So a sort is happening inside of these lists here. But the important thing is that if I print A, nothing has changed. So the list is still the original one. Whereas if I call a.sort, it has the exact same effect, but it's actually applied to the array. So that's the difference. A.sort is the same as saying A equals np sort. So A equals np sort A is the same thing as calling a.sort. But you can sort in different ways. So for example, this here by default, I think sorts on axis 1, if I'm not mistaken. So if I run this here, that's exactly what's happening here. So it sorts it inside of this list, or inside of these lists. If I say axis equals 0, it's going to sort it here in the column. So now 5, 4, 7 turns into 4, 5, 7. So it's sorted vertically like this. And 9, 1, 3 becomes 1, 3, 9. As you can see, 1, 3, 9. And here we get 2, 6, 8. Now, of course, you can call them one after the other. So you can say np sort, first sort axis 0, then sort axis 1. And this is going to result in sorting it on both axes. But you can still see that that's not the same as just saying give me all the values in ascending order here. So that's not always the goal. In this case now we sorted by column and by row, but it still doesn't mean that the 3 is now all of a sudden going to magically move into the first list. If you really want to get the same sort that we had before, one thing that you could do for whatever reason, if you want to do this, is you could flatten the array. So you could say a flatten, which would give us, of course, a list like this. Then we could sort this list, and then we could reshape that back into the shape of A. So we could get the shape of A, and then we would get 1, 2, 3, 4, 5, 6, 7, 8, 9 if you want to. So these are the two ways in which you can sort NumPy arrays. This is just something I wanted to cover here. The next thing is, how do we search for values? And searching, basically, it's not really a searching like give me an index. It's more like we can locate specific values and we can get certain indices for them. And the one or the couple of things that I want to show here are the things that are going to be particularly relevant for machine learning, because oftentimes you train a neural network and you get some results in the end, some softmax outputs, for example. For those of you who don't know what softmax is, this is now machine learning, not NumPy. A softmax function gives you the probabilities for the individual classes. So for example, if you have a model that, let's say that we have some outputs of the model, and the model gives you some probabilities for the individual classes, and if you have 10 different digits that your image could be, you get a probability for each digit. So you get 5 values, something like, actually I have some values prepared here so that they are consistent. So let me just copy them. Actually, I don't think that these are 10, but we can imagine that they're 10. So how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8. Let's say you have 8 classes. These could be images like cats, dogs, horses, deers, whatever. Let's say they're just animals, and then you classify an image, and as a result, you get the highest percentage here. So 87% for a cat, for example. And the idea now is that what you want to have from this output is you want to know, okay, where is the highest value? What's the index of the highest value? Now, of course, by just looking at this, you get the index 2, obviously, but sometimes you want to do it in an automated way, or you want to do it for a high dimensional array. So what you can do here is you can use the function called argmax. So np argmax will give you the index of the highest value. So if I say outputs, I will get here 2 because that is the highest activation. Now, maybe I also want to have the lowest activation. So if I have the lowest activation, I can get that with argmin. This will give me now the index 6 because that's the 0. But if I have multiple 0.01, for example, which is the lowest value, but I have it like 4 times now, I will just get the first index. So I will get this one here. So this is what you can do with argmax and argmin. Now you can also say print np non-zero, and this will give you the indices of non-zero, actually outputs non-zero values. So it will give you all the indices of values that are not 0, in this case all of them. But if I change this to 0, for example, I will not get the index 6. So this is important maybe if you want to avoid zeros. And also you can specify conditions yourself by saying np where, and then you can say, for example, outputs is larger than or greater than 0.01 in the outputs array, and you want to return a 0 if it's not the case. So in this case, we would get now the values or 0 if it's below 0.01. So this would be useful, for example, if you want to say, okay, below a certain threshold, just do everything to, or truncate everything to 0, and otherwise just return the value. This is what this function can do. And again, if you want to go into more details here, there is a NumPy documentation page, sorting, searching, and counting, where you can look into the individual functions here. Next up, I want to talk about iteration, so iterating over arrays. And for this, we're going to generate an array A by calling a range. We're going to generate 12 values, and we're going to reshape the array to 3 and 4. This will give us an array like this, 0, 1, 2, 3, 4, 5, 6, and so on. And we can now iterate over this in multiple ways in terms of syntax, but also in multiple orders or in different orders. So one way to iterate over this is to say 0, 1, 2, 3, 4, 5, 6, and so on. Another way would be 0, 4, 8, 1, 5, 9, and so on. So these are different orders in which we can iterate, called row major and column major. And one simple way to iterate over an array is to say for row in A, for element in row. And this, of course, works easily if it's like 2-dimensional, but you have to have like an additional loop for every dimension. So you need to say for row, for column, for n dimension, whatever, until you get to the element, and then you can just print the element. So this, of course, works. Let's print here with a space so we have everything in a row. This, of course, works, but it's tedious and it's not the professional way to do it. The professional way to do this is to use np nd iter, so an iterator. So here what we do is we say for element in np nd iter, and we pass the array, and then we print the element, and this has the exact same effect in this case. So actually we want to print a line break in between, but you can see that the result is the same. And it also works for higher shapes. So if I go with something like 24 here and I say 2, this one here will give me some funny iteration, whereas the nd iter approach will still give me the proper iteration. So this is flexible and it doesn't really break if you go into higher dimensions, and you don't have to manually come up with additional loops here. So that's a professional way to do this. What you can do here also is you can specify the order. So the default order, I think, is C. I'm not even sure what C stands for, to be honest, but you pass order equals C, and I think that's the default way. So 0, 1, 2, 3, and so on, the row major way. And if you pass F, this stands for Fortran mode, and it iterates in a column major way. So 0, 4, 8, 1, 5, 9, as you can see down here. So I don't really know why you would use that, but maybe you come up or you encounter a use case where you want to do this. Another thing that you can do here is you can also specify a certain flag that allows you to change elements. So if I do this now by default, if I say for element in nd iter a, and now I want to change the element, what happens here is I can say, for example, element equals element squared if I want to. And I'm not sure if this is going to run. We can take a look at it. It does run, but it doesn't change anything. So this code is executed, but as you can see here, nothing changes. I still have the same array as before. But what I can do is I can use nditer to allow writing access. So I can say here with np nditer on the array, and then I can pass op flags is equal, and now I can pass a list here with read write as a string in it, as it for iterator. And then I can do the same thing as before. I can say for element in it, and I can say element, and now I can use here square brackets with 3 dots is equal to element squared. And then I can print the array. And when I run this, you can see that the numbers are squared. So this is also something that you can do. I'm not really sure how best practice, or if this is considered a good practice, but this is a way in which you can do that. You can iterate and also change the values. And of course, we also have a documentation page here, so iterating over arrays, you might want to look into this one for more details. Now, next up, I want to talk about masking. And masking is something that you can do if you want to exclude certain values of your array from calculations, from being processed, without having to replace them or without having to remove them. So for example, let's say I have an array, and in this array I have a bunch of values like 1, 2, 3. Then maybe I have a nan value in here, so an invalid value, not a number. And maybe I also have something like infinity, or even if I have valid values, maybe I want to exclude certain values from being used in calculations, just because I have my reasons for it. So if I try now to say array.mean, the problem is I get nan, because there's a nan value involved here. And even if I replace that, I will still have infinity, and infinity will mess up the calculation. Now, there are scenarios in which I don't want to replace these values. I don't want to get rid of them, but I don't want to use them in calculations for the mean, for example. Or maybe I have some outliers that I also don't want to get rid of, but I don't want to use them in the mean calculation. So what I can do in this case is I can use a masked array. So I can say import numpy .ma as ma, and I can create a masked version of this array. So I can say masked array is equal to ma masked array, and I pass here array, and I also pass a mask. And the mask is a list containing zeros and 1, 0 meaning that the element at this position is not masked, and 1 means it's masked, so it's excluded from calculation. So for example, 0, 0, 0, then a 1 for the nan value, 0, and a 1 for the infinity value. If I now go ahead and say masked array.mean, you will see I get 2.5, because that's the mean I get from 1, 2, 3, and 4. That's the mean of these 4 values. And I can also print the masked array itself, and you will see what it looks like is I get 1, 2, 3, then nothing, 4, and nothing. So that is how masking works in general. And this can be very useful, as I said, if you want to exclude certain values from the calculation, but you don't want to necessarily remove them from your array. Maybe you just want to use them for one specific action, and you also don't want to replace them with, you don't want to impute them with a 0 or a -1 or something. You want to just exclude them from the calculations. That's the purpose here. We can do the same thing with sum, and as I said, you can also do this with any other values. So you can also do that, for example, with a 3. In this case, I would get 2.3. Or 7 as a sum here, because the 3 now is no longer included in the calculation. So it's just 1, 2, 4, and then that is used for the mean and the sum calculation. This can also be done with multi-dimensional arrays. So if I have array is np array, and then I have 1, 2, 3, 1, 2, 3 like this. Come on, mistyping way too much here. 4, 5, 6. That's the array. Now I can create a masked version of this. So masked array is going to be equal to ma masked array, and now the mask, of course, has to have the same dimensionality. So I have to say, for example, 0, 0, 1, and 1, 0, 0. This would now exclude 3 and 4. And if I now say masked array sum, print this. Then, of course, I get just 1 plus 2 plus 5 plus 6, and that is 14. All right, so that is how you can do that with multiple dimensions. Also, you can get from a masked array the mask if you're interested in that. So if you already have a masked array, you can say get mask. Or actually, you do this the other way around. You say ma get mask from a masked array. This will give you the mask. So you can also pass booleans, of course. And the important thing, or the useful thing now, is you don't have to do this manually. You can do it manually, but there are also methods that you can use to do this easily without having to manually specify zeros and ones or trues and false. You can just say, for example, that you want to create a masked array, but not a masked array by specifying a mask, but for example, by saying masked greater. So masked greater would mean I pass an array and I say that everything above 4 should be masked. So the result of that would be I get 1, 2, 3, 4, and then nothing, nothing, because 5 and 6 are above 4 or greater than 4. I can also specify an interval. I can say masked inside. So everything between a certain range should be masked. For example, 2 and 4 would be 1, 5, 6 as a result, because 2, 3, and 4, including 2 and 4, as you can see, are masked, so not used for the calculations. I can do the same thing with outside, which would be the opposite, obviously. So I would get 2, 3, 4 are not masked. Everything else is masked. I can do also the same thing with a where condition. So I can say, for example, mask from array, or actually I pass the array as the second parameter here. The first one is the condition. And for example, the condition could be array modulo 2 equals 0. So I only want to mask the even value, so I want to only use the odd values here. Or, which is useful for the thing that we talked about before, we can also mask invalid values. So I can say, for this I don't need any additional parameters. I can just say masked invalid and pass an array. And in this case, I of course need to have invalid values, np_nan. I'm not sure if infinity is masked. I think so. np_inf, let's see. Yeah, there you go. These two are masked now because they're invalid. So you can also use functions like this. You don't have to specify the mask yourself. And of course, as always, there is a documentation page for all the details. Now, the next thing I want to talk about is the difference between a view and a copy in NumPy. Now, what happens when I select a certain portion of an array and save it into a new object? So let's say I have array equal to np array 1, 2, 3, 4, 5, and then I create a new array and I say that this is just a portion, a selection, 0 to 3, for example. So obviously, new array is now a new Python object and it only contains the values 1, 2, 3, not 1, 2, 3, 4, 5. So is this now a view or a copy, and what's the difference? Now, this right here in this particular case is a view, and a view is basically just a different viewpoint onto the same data. So it's the same data, the same underlying data, the exact same thing in the memory, but from a different perspective with different metadata. And the reason this is important is that if I now go ahead and say new array, index 1, for example, equals 100, then of course, when I print new array, I'm going to get the change. But what's also going to happen is if I print the original array, you're going to see that now the value here has changed as well. Because I'm not actually working on a copy, I'm working on the exact same data, on the same underlying data. It's just that I have a different view on it. I'm looking at a different metadata object, you could say, but I'm still looking at the same underlying data, which means that if I change something about it, it's actually going to change the original data as well. Whereas if I say, for example, that new array is array.copy, I can explicitly make a copy like this, and then I change new array to be equal to new array 0 to 3, then it doesn't have the effect, because now I'm first creating a copy, meaning I'm copying the data to a different point or to a different space in the memory. Now I have different underlying data. I still select the same slice and I still have the same array selection, so to say, so I still have the same values. I can still update the value to 100 and I still get the result in the command line, but the underlying or the original array here is not changed. So I'm not working on the same data here. And it's important to know when you get a view and when you get a copy. For example, when you do slicing, you always get a view, but if you do advanced indexing, you always get a copy. So if I say new array is equal to, let's maybe use again lists here 4, 5, 6. If I use advanced indexing to select certain values from here, then the result of that is always going to be a copy. So if I say, for example, 0 and 1 here, and I print new array, what I get here is I get a, actually I don't want to do 0 and 1, or actually I do want to do 0 and 1, but let's go then and say we have 7, 8, 9 as well. Then I get a certain selection, a certain subset of the array, but this now is a copy, which means that if I change something about it, it's not going to change the original array. If I say new array, change 0, 0 to 100 or 1000, whatever, print new array and print array, you're going to see that the changes are not applied to the original array because advanced indexing always returns a copy. And there are rules like this, but an easy way to figure out if you're working on a copy or a view is to look at the base attribute. Now, if the array is the original array, or if the array is a copy or the array itself, the base object is none. So if I print array.base, here I have no base. This is a separate array. If I say now that I want to print array copy base, I also get none because that's a separate array. But if I create a view onto an array, it's not the array itself, it's a view onto the array and it has a certain base array. So if I say print array, then I select the section 0 to 2. From that, the base object is the base array. So base points to the underlying data. So if I have a view, the base object or the base attribute is not none, it points to the original array. And if I have a copy, a separate array in and of itself, this is none. So I know it's a copy or an original array and not a view. Another important thing in NumPy is vectorization. Now we all know what happens when we call a function like the sign function onto an array like this one. When I say print np sign array, what happens is the sign function is applied onto all of these values. Now, this can work with multiple different functions. We can do that with sign, we can do that with exponentiation and so on. But what if we want to define our own function to do that? Let's say I want to have, I want to define a function. Let's call it square if even. And this function takes a value as an input and returns if x modulo 2 equals 0. And this can be whatever function you want. But if x modulo 2 is 0, then I want to return x squared, otherwise I want to return x. So that is my function, and now I would like to apply this function onto the array. This doesn't work out of the box. If I go ahead and say square if even array, you're going to see that there is a value error. I cannot do that. I cannot just go ahead and use this function onto an array. What I need to do in order to make this possible is I need to vectorize it, and this can be done very easily. I can just say np vectorize square if even. I can pass the function here as an object, and as a result here I get a vectorized square if even, if I want to call it that. And then I can call this function onto the array, and this works now. So the only thing I have to do here is I have to vectorize it, and then I can apply my function onto a NumPy array. So it works like np sign, it works like np exp, and so on. So you can define a function like this that takes a value and returns another value, and you just have to call np vectorize onto it to make it compatible with NumPy so that you can call it on arrays. Now for the next concept, I already copy pasted my prepared code here, so I don't have to type this and waste a lot of time. The thing I want to talk about here is a specific operator. I also have a separate video on this channel about this operator, which is the matrix multiplication operator. It was introduced in Python 3.4. And the basic idea is if you have two NumPy arrays, which are matrices basically, you can, of course, calculate the matrix multiplication manually like this, or you can call, of course, the np matmul functions for matrix multiplication, where you pass a and b. And you're going to see that the results here are the same. So if I do it like this manually, if I do matmul AB, I get the same result. And there's an operator that a lot of people don't know about in NumPy. What you can do is you can say print a and then at, so the at operator b, and this is going to result in the exact same thing. This is going to perform a matrix multiplication. A matrix multiplication b can be written like this. So this is an interesting thing to know if you didn't know about this. All right, now the last thing I want to talk about in this video today is custom data types in NumPy. What we can do in NumPy is we can define our own custom data types, and this can be very useful in terms of memory and performance optimization. Now, what happens in NumPy when I create an array? If I have a basic array with a bunch of integers in there and I print the data type of that array, it's going to be integer, just because NumPy decides it only contains integer, so the data type is int64. Now, if I change one of them to floats, all of them become floats, and the data type of the array is float64. If I now add a string to it, all of these values become strings, and the data type of the array is, we're going to talk about this notation here in a second, but it's a string basically. It's a Unicode string with a maximum of 32 characters. Now, if I add something more complex, like a dictionary with a key and a value, this becomes an object because it's now too versatile. It's just an object and that's it. Now, what we can do in NumPy is we can define our own data types and we can explicitly set them, we can specify them, and sometimes this makes performance and memory differences. So what I can do in NumPy is I can say dt equals np dtype, and I can pass here a NumPy data type, for example. I can say np int32. And this is now a data type object that I can pass, for example, when creating an array. Now, this is, of course, an already built-in one, so I can say stuff like dt name, and this will give me the name of this data type. I can also print dt type. This will give me the NumPy class or type, which is NumPy int32 again. I can also print the byte order, which is either little endian or big endian or just a hardware native. So byte order in this case, it's going to be an equal sign, which stands for native. A greater than sign or a closing bracket is a big endian, and the other one is little endian. And then we have also dt, I think it was item size, which tells us how many bytes this occupies. Obviously 32 bits divided by 8 is 4 bytes. So this is how you can get information about the data type. Now, this is not the only way to specify a data type. You can also specify a data type as a string. So for example, I can say equals I4 to define the exact same data type. This would be hardware native byte order, so whatever the hardware is, I for integer, and 4 for 4 bytes. This would result in the exact same data type. Now, here it makes sense to look into the documentation because there's a table explaining how this notation works. We have a bunch of characters here. For example, I for the signed integer, U for the unsigned integer, and we also have capital U for the Unicode string. So for example, what I can do here is I can say I want to use U and then a number, which is going to be the number of characters. So 10, for example. That is going to be my new data type. And when I now look at it, you can see it's a string 320. Why is that? Because I have 10 characters, 1 character is 4 bytes. So 10 times 4 is 40 bytes that I'm using, which is what you can see here for the item size. Times 8 is 320 bits. So the data type is string 320 because that's the amount of bits that we need for this one. Now, what happens if I define a NumPy array full of strings and I pass this data type? So if I have, for example, hello world, how are you? What happens by default here is, first of all, I can print the array and I can also print the data type, the default data type, and you can see that I just get the values, and the default data type here is U5 because there is no string that has more than 5 characters. So it doesn't have to be U10. But if I extend a word, so if I say hello with a bunch of O's here, you can see that this increases to U17. Now, if I specify the data type here, if I say dtype is explicitly equal to dt, now the data type is U10, even though I only have 5 characters max. But if I now extend this word to a very long length, or to a long size, you can see that it truncates the O's. So maybe it's better to see that if I type a bunch of values here, whatever, you can see that at some point it truncates the string because the maximum amount is 10 characters here. That's a specific data type that we're setting here. Now, this is just a small example, but we can also define very complex data types. So for example, if I have an array where the individual element of that array is a tuple with a bunch of different complex values in there. So let's say one entry in my array is a tuple that starts with an integer like 16, then it continues with a NumPy array in and of itself. This NumPy array then has, let's say, two lists with 3 values, so 2.7, all of these are floats, 8.7, and then here I have 1.1, 9.2, 12.32, whatever. And then after this array, I also have a float again. Then this is one entry. And now let's say I have multiple of these entries, all of the same structure. Then the data type of this array can be defined dt equals np dtype. It can be defined by a string. I can say that this is an I4, comma, a 2x3 F8 array, so float with 8 bytes, followed by a float with 4 bytes, for example. So this would be a 32-bit float, and this would be like a double. This would be a 64-bit float. And that would be the data type for this specific array. So I can say dtype equals dt. And that would then work and also be shown as a data type, as you can see. So that is how we can do that. And sometimes this leads to performance difference. So I'm not sure if it's going to lead to a performance difference here, but I'm going to try it. We're going to define, for example, the data type dtype, and we're going to say we want to use U5 here, followed by F8. And then we're going to say, or actually let's go with F4. Then we're going to say that the array 1 is going to be an MP array, and we're going to have the values here, a tuple, hello, and a number, 29.1, for example. And then we're going to have world and 32.1, for example. And then we're going to have the last value, how, and then let's say 1431.1. And we're not going to specify any data type. And then we're going to do two other things. We're going to say here, we're going to specify our own data type, dt. And here we're going to specify that we want to force this to be an object, so a Python object. Now the results here that we're going to see don't have to be always the case. So it's not the case that it's always the most efficient to use whatever ends up being the most efficient one here. But we can see which one takes up how much space. First of all, let's print the data types. So array 1 dtype, array 2 dtype, and array 3 dtype. And you can see we have here a U32. So first of all the floats are being typecast to strings, which is oftentimes not what we want. We want to keep them as floats, if possible, sometimes. Here now you can see that I get this data type here, and then I also get object. So if I want to see how many bytes are occupied by the individual arrays, I can just say array 1 n bytes, and I can do that for all of these arrays. And then we can see that the first one, the automatic data type, takes 768 bytes because all of these are now strings. The second one takes 72 bytes, which is much, much better. And using object in this case takes 48, which is the most efficient. But this is how it makes a difference. If you don't specify anything, you might run into inefficient memory usage, into also typecasting that you don't want to. So specifying a data type explicitly is oftentimes necessary and oftentimes good for performance. So that's it for this advanced NumPy course today. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and